Hello, ChemComm. The last time we were together, we took a look at the mole, and we talked about how 1 mole equals 6.02 times 10 to the 23rd atoms and molecules. Today we're going to take a look at how the mole also equals the gram atomic mass, or the gram formula mass, of an atom or a molecule. Let's get started. So just to review, in 5.5 we talked about how a mole of a substance is equal to 6.02 times 10 to the 23rd particles of that substance. Today we're going to show how the mole of that substance should also equal the molar mass of that substance. The way we find the molar mass is by finding the formula mass of that molecule, or by just looking up the atomic mass on the periodic table. Typically, it's very hard to count atoms in a chemistry lab. That's why it's much easier to find the mass of those things and then figure out how many atoms or molecules we have based on the mass. Remember, the mole is considered the chemist's dozen. The mole is just a term that tells us how many, 6.02 times 10 to the 23rd. The formula mass is the sum of the masses of all the elements within a compound. We've done this before when we did percent comp, so this should feel familiar. The molar mass is simply equal to 1 mole of the substance. It's found the same way as the formula mass, and it's what we use in lab to determine how many moles we are using in lab. Just a quick review on how to find the formula mass or the molar mass. You're going to list your elements, you're going to count how many atoms of each element, and then you're going to look at the atomic masses on the periodic table and multiply by how many you have and add them all up. That should give you the molar mass. Let's try a couple. Fluorine. Notice in this one there is only one fluorine atom, and therefore all we have to do is look at the periodic table and write down the molar mass. And on the periodic table, the molar mass of fluorine is 19. But let's suppose we have a fluorine molecule. In other words, F with a subscript of 2, telling us there's 2 fluorine atoms. In this case, we'd take 2 times 19, and we would get 38 for the total mass of this molecule. Here's a much more complicated one. So let's list out our elements. We have magnesium, we have phosphorus, and we have oxygen. There are 3 magnesium atoms. 2 times the invisible 1 subscript here means there's 2 phosphorus, and 2 times 4 here would mean there's 8 oxygen. Now we need to multiply by the mass of each element. Now that we have the mass of each element, we can add them all together to get our total. And we get a total of 262.87. So that would be the molar mass of magnesium phosphate. So the question is, how do we use this in a lab setting? If you remember the graphic organizer we've been using, we've gone from particles to moles. Well, today we're going to look at when we go from moles over to mass. And notice in the equation, molar mass is the part of the equality that we need to use. This problem says how many moles are in a 45-gram sample of SO2. Since we know we're dealing with grams, we know we're going to need the molar mass of SO2. Let's calculate that first. So we can see that the molar mass of SO2 is 64.1. Now we're going to start our dimensional analysis problem with 45 grams. Since grams is the known unit, that means grams is going to go on the bottom and moles is going to go on the top. And I know that 1 mole should equal the molar mass in grams of this substance, 64.1. In other words, I'm going from mass to moles, and therefore I should be using 1 mole over the molar mass, which is exactly how I have set up. The way you'd put this into your calculator is 45 grams divided by 64.1, and that would give us 0.702 moles. So it's very similar to using Avogadro's number, it's just we're using the molar mass instead. Here's another example. Since we're using grams, we should find the molar mass of HNO3 first. That gives us 63.021, and our given we'll start with is 0.0718. In this case, moles goes on the bottom, and grams goes on the top. And our equality is 1 mole equals 63.021 grams. So if we look at our diagram, in this case we're going from moles to mass, which means we should be multiplying by the molar mass, which is exactly what we're doing. So now we can take our moles and multiply by our molar mass. And we get 4.52 grams of HNO3. So now that we've done the two types of problems that we need to focus on, going from mass to moles and moles to particles, we can combine the two. This problem wants us to go from grams of gold all the way to atoms. What that means is we're starting here at mass, we're going to go to moles, and then we're going to go from moles to particles. And we can use the equalities right on the chart to help us do that. So our given is 3.4 grams of gold, which means we're going to do 1 over the molar mass. 1 mole over the molar mass of gold, and we can look that up on the periodic table, and it is 197. And then when we go from moles to particles, moles goes on the bottom, 1 mole, and 6.02 times 10 to the 23rd goes on the top. The way we'd put that into our calculator is 3.4 divided by 197 times 6.02, and then we'd hit the EE button, and then 23. It'd look like this. And that gives us 103 times 10 to the 22nd. And that would be atoms of gold. So these problems are just like the dimensional analysis problems we've done in the past, where you have multiple steps in the same problem. Use your flow chart to kind of help you know which equalities to use. It'll be a big help to you. This last example is one going in the other direction, from molecules all the way to mass. I'm going to let you do that on your own, but if you have questions, make sure you ask. I know moles can sometimes be difficult, and sometimes it's easy to get lost in the math. Make sure you're putting in enough time to understand this stuff well. Do the practice problems. Let me know if you have questions. Good job today. We will see you soon.